You press Ctrl+C every single day. A script is hanging, a server won't stop, a command is taking too long, you hit Ctrl+C, and it dies. Simple, right? But have you ever wondered what actually happens in that split second? Between your finger hitting the key and the process disappearing, there are 5 distinct layers of your operating system working together. Today, we're going to follow that signal on its entire journey, from hardware, through the kernel, all the way to the process. Let's go. It all starts with hardware. When you press Ctrl and C together, your keyboard generates something called a scan code, a tiny number that identifies which keys were pressed. The keyboard controller packages this scan code and sends an IRQ, an interrupt request, directly to the CPU. Now here's the important part. The CPU literally stops what it's doing. It saves its current state and jumps to a special function called the keyboard interrupt handler. This handler reads the scan code and figures out which keys were pressed. It recognizes the combination as Ctrl+C. And this is key, it doesn't kill anything. It doesn't even know which process you want to stop. Instead, it passes this character to the next layer in the chain, the terminal driver. The character arrives at the kernel's TTY subsystem, the terminal driver. And this is where things get interesting. The TTY layer is not just a simple pipe that forwards characters to programs. It's an active processor. It watches every character that flows through it, looking for special sequences. When it sees Ctrl+C, it checks its configuration. You can actually see this configuration yourself by running sdty- in your terminal. There's a setting called inter, short for interrupt, and by default, it's set to Ctrl+C. Here's what the TTY does next. It swallows the character. Your program never sees it. Instead, the TTY generates a signal, specifically SIGINT, signal number 2. But it doesn't just send this signal to any random process. It needs to figure out exactly which processes should receive it. And that brings us to one of the most misunderstood concepts in Unix, process groups. When you open a terminal, your shell creates something called a session. Within that session, processes are organized into groups. Think of it this way. When you run a pipeline like cat, pipe to grep, pipe to sort, all 3 of those processes belong to the same process group. They're a team working together on one job. Your shell keeps track of which group is in the foreground, meaning which group currently owns the terminal. When the TTY generates SIGINT, it sends the signal to every process in the foreground process group. Not just one process, all of them. This is why Ctrl+C kills your entire pipeline, not just grep or just sort. The whole group gets the signal. And here's the flip side. If you started a process in the background with an ampersand, it belongs to a different group. It doesn't get the signal. Ctrl+C can't touch it. Now the signal has been sent. But how does a process actually receive it? You might think the kernel just pauses the process and delivers the signal immediately. But that's not how it works. Inside the kernel, every process has a data structure that includes a signal pending bitmap, basically an array of bits, one for each possible signal. When the kernel wants to deliver SIGINT, it simply flips bit number 2 from 0 to 1. And then, it waits. The process keeps running, completely unaware. The signal only gets noticed at a very specific moment, when the process transitions from kernel mode back to user mode. This happens after a system call, after a timer interrupt, or after handling I/O at that transition point. The kernel checks the pending mask. It sees bit 2 is set, SIGINT is waiting. Now, and only now, does it take action. And what action it takes depends on whether the process has set up a signal handler. Every signal has a default action. For SIGINT, the default is simple: terminate the process. No questions asked. The process just dies. But programs can catch SIGINT by registering a custom signal handler. A web server, for example, might catch SIGINT to close all active connections gracefully. A database might catch it to flush pending writes to disk. A training script might save its checkpoint. In Python, it looks like this. You call signal.signal with the signal type and your handler function. When SIGINT arrives, instead of dying, your handler runs. It can clean up resources, save state, print a goodbye message, whatever you need. After the handler finishes, the process can choose to exit cleanly or even continue running. But there's one signal that no process can ever catch: SIGKILL, signal 9. When you run kill-9, the kernel doesn't check for handlers. It terminates the process immediately. No negotiation, no cleanup, game over. When SIGINT's default handler terminates a process, the process exits with a specific status code, 130. That's 128 plus the signal number, and SIGINT is signal 2. The parent process, usually your shell, has been waiting for this moment. It called a function called wait, which blocks until the child process exits. When wait returns, the shell receives the exit status. It decodes it and knows my child was killed by a signal specifically SIGINT. The shell then prints a new prompt and hands control back to you. You can actually verify this yourself right after pressing Ctrl+C, type echo $? You'll see 130. And just like that, the journey is complete. So let's trace the full journey one more time. You press Ctrl+C. The keyboard sends an interrupt to the CPU. The CPU's handler passes the character to the TTY subsystem. The TTY recognizes it and generates SIGINT. The signal is sent to every process in the foreground group. The kernel sets the pending bit. On the next transition back to user mode, the signal is delivered. The handler runs either the default termination or your custom cleanup code. The process exits, and the shell gets its prompt back. 5 layers, 1 keystroke, a beautiful chain of systems working together. If you enjoyed this, like and subscribe for more deep dives into how your operating system really works. Thanks for watching.